Hello students. So in this video we are going to discuss about the important result of uh, rolling on inclined plane. Rolling motion on inclined plane. Okay. So let us take that there is a inclined plane and the angle of inclination is theta, and let us consider that there is a round object. Okay, and this is a body, and we can see what are the forces acting on pure rolling. We are considering pure rolling. Okay, when we are saying here rolling, that means pure rolling. No sliding action happens. If it is just sliding action and no rolling action is there, then you know the important result. Just like there is a friction or no friction, you can consider pure sliding. Pure sliding is just like a point mass, a point object, but rolling here involves both kind of motion. As we have discussed, it involves rotation as well as translation motion of center of mass, right? So what are the forces acting, and we can calculate what will be the acceleration of the center of mass in this direction. There will be acceleration of the center of mass, that we have to calculate, right? So if you see the forces, let me draw this diagram more clearly and bigger way so that we can see the effect of forces. So if you see the forces acting the center of mass, mg force is acting downward, right? Mg, and if there is a friction, in which direction friction will act, isn't it? So normally let us say you are keeping the object, and if friction is not there, then what will happen? This will try to just slide. So then what will happen? This force of friction will act in opposite direction, right? So force of friction will act in this direction. So consider this is the direction of force of friction. So two forces you can take. Another force you can take is mg. Mg is already done. Normal friction, and this, right? So the line of action of the normal passes through the center of mass. This is the center of mass, right? Friction is so if you consider the rotational effect about the center of mass, then which force is creating torque? Because mg does not create any torque about center of mass, because it is line of action is passing through that, isn't it? And normal also is not going to create any torque about center of mass, but friction is going to create torque. Okay, so friction is getting creating a torque, and let's say this is the radius. So the torque created will be, of course, in this direction. There will be angular acceleration. So that torque, which is in anti-clockwise direction, here is friction into r, right? That's the torque. Okay, so because of this torque, there will be rotational effect, and what will be the acceleration? So you can study the forces and accelerations both. So what is the net force acting on this? So if you see the resultant force, let us draw the vector diagram forces. So mg is acting this. I am just drawing the forces, only vectors. Force vector I am drawing. Friction will be this, normal will be this. This is just force vector, but this is not the actual diagram. Actual diagram is shown here in this figure. So this force here, what is the net force? So mg you can resolve here, and this is the theta, right? So mg cos theta, mg sin theta, right? All this effect you can study, and you can see what is the net force. It is under rolling motion, so mg sin theta minus f, that friction also you need to subtract. Okay, so here you cannot say that friction has to be 0 because it is pure rolling. It is not uniform pure rolling, it is accelerated pure rolling. So this is the case of accelerated pure rolling. You can Note, it is the case of accelerated pure rolling. Accelerated pure rolling. So friction will be acting, okay, and the torque will be acting, okay. But in accelerated pure rolling, the condition, if you remember, the condition is acceleration of center of mass is r into alpha. This condition we can apply, isn't it? Right. So let us calculate this torque. Torque is friction into r. And what about the net force? Net force you can write as mg sin theta minus friction, because normal will balance mg cos theta, right? So mg sin theta minus friction, that is the net force, which is mass into acceleration of the center of mass. And here acceleration means acceleration center of mass, okay. Mg sin theta minus friction. Okay, so from here I think acceleration we can calculate. What will be acceleration from here? Acceleration will be g sin theta minus friction by mass, right? And r into alpha. Alpha from here, torque equations, you can calculate alpha from torque equation, right? So let's use this torque equation. So torque is I into alpha. I is I center of mass, is equal to F into R. So let us substitute here. I center of mass, what is I center? Let it be, right? So alpha you can calculate. So alpha is equal to F into R by I center of mass. So let us substitute here this acceleration of center of mass, which we calculated from force equation, and from torque equation we calculated. If you substitute it here, what do you get? Here let us substitute this. So this acceleration is g sin theta minus F by mass, and R into alpha. Alpha is Fr by I center of mass. So from this, let us try to solve this equation. Okay. Now what do you get from here? I think we can try to calculate friction, isn't it? Try to calculate friction from here. So g sin theta minus, or you bring that side, so friction can be taken common. So friction by mass, or mass you can take LCM and then try to simplify this, right? Take LCM this side. So this is g sin theta mg sin theta minus friction is equal to mr square into friction by I center of mass. So bring friction one side and try to solve it. 1 plus mr square by I center of mass is equal to mg sin theta. Okay. So from here friction can be calculated. Friction will be mg sin theta by 1 plus mr square by I center of mass, right? We got friction. Now if we got friction, now acceleration center of mass we can calculate from this equation. You may note this as equation number 1, equation number 2. You can substitute this here, F by m. Let us substitute this to calculate acceleration center of mass. So from equation first, acceleration of center of mass is equal to what it is? G sin theta minus F by m. Let us try to calculate G sin theta minus F by m. So G sin theta minus friction by mass, that becomes G sin theta 1 plus mr square by I center of mass. I think now you can take G sin theta common and just check what do you get. G sin theta you take common, 1 minus this ratio, right? So 1 plus this minus 1. So I think in the numerator you will get mr square by I center of mass, and here it will be 1 plus mr square by I center of mass. I think you can divide it by that factor. So acceleration of center of mass you get as g sin theta 1 plus I center of mass by mr square. That's the important result, right? That's the important result. So this is an important result, this is an important result, all these are important results, okay, on this. So here now I'll tell how to write this or how to remember this. So what you can do is you can remember acceleration of center of mass in terms of g effective. Here you can define a term g effective, and acceleration of center of mass is g effective sine theta. You can write g effective sine theta, where g effective can be written as g divided by 1 plus I center of mass by mr square. Okay, so this is what it is, g effective, and you can just substitute here and calculate. Okay, so let us summarize this result. Basically, acceleration of center of mass is an important result here. Okay, so let's summarize here. So acceleration of center of mass, if this is an inclined plane and you are considering pure rolling of a round object, then acceleration of center of mass is given by this formula, g effective into sine theta, where g effective is g by 1 plus I center of mass by mr square, where m is the mass and r is the radius of that. And if you want to calculate, then angular acceleration can also be calculated, angular acceleration, because it's going to rotate, so there will be angular acceleration. Angular acceleration, so center of mass by r, right? So just divide that by r, you will get it, isn't it? This is g effective sine theta divided by radius. That g effective here already we have calculated. Okay, because it is pure rolling, so we can use these conditions. Now here there are some important results, like for example, what will be the velocity when it will reach at the bottom, how much time it will take, and how much distance it will travel. Everything can be calculated by just considering this acceleration of center of mass. Okay, so if you calculate the velocity that it will achieve at the bottom, what velocity it will achieve. Finally, initially, let us say you have released it. So initial velocity u is 0. Center of mass is 0 velocity, right? So v center of mass at the bottom is equal to u plus 80, right? U plus acceleration center of mass into time. Or if you want, you can use, but time is, let us say, not given. So v square equal to u square plus 2s you can use, and here height or distance you can take. For this distance you are going to take this, let us say the distance is x. So v square equal to u square plus 2s, so v is equal to root under 2 acceleration into distance. Now here acceleration can be written as 2 into this one, g effective sine theta into x. Okay, and suppose the height is h. For example, suppose this is the height from which it is released. So this height is x sine theta. So x sine theta can also be written in terms of h. So the velocity of center of mass is root under 2g effective into h. And g effective is what I have already told. So this is what is velocity, you can remember. Similarly, you can note the formula for time. Time is root under 2gh. So here root under 2g effective root 2h by g, right? So root under 2h by g. So h by g effective. Okay, like this you can do. Or here you may also write this as root under 2 x by acceleration, which is effective acceleration center of mass, right? Because once you substitute here acceleration as g effective sine theta, and x can be written as in terms of that, right? So you will be able to write this h by x sine theta that will become correct. Or if you want, you can try to derive it. It's not very difficult. Let's say you can take this x is ut plus half ut. So x is equal to ut u0 half acceleration center of mass into t square. So time will be root under 2x by acceleration of center of mass. Correct. This will be the formula, time formula. And here you can of course substitute now in terms of height. If you want, you may try to substitute it, right? So if you want in terms of so x is equal to h by sin theta, it will be correct. You can substitute it here. So time will become root under 2 x is h by sin theta, and g acceleration is g effective sin theta. Okay, so sin theta factors will come out. Okay, so time formula little bit different. It is root under 2 h g effective, and the sin theta will come outside. Okay, so sin theta is going to come like here outside, 1 by sin theta. So this is little bit different. So analogy we can use, but sin theta factor we have to divide. Okay, this is the second formula for time which you can remember. Second formula for time. Okay, I think mostly this is what they can ask you. Generally theta is not changing. Theta is a constant for a given plane. But if there are comparison between two inclined planes, right, then you can use this result. Okay. So I think with this you will be able to solve questions. Let's take one simple example about what type of questions can be asked. So suppose if there is an inclined plane and this is angle of inclination theta, let us say it is 60 degree, and there is a round object which is released from here, and initial velocity is 0, so center of mass is going. So now suppose if I take two different objects, first case I can take a solid sphere, and second case I take a hollow sphere. So let's say the time taken by the solid sphere is t1 to reach the bottom, and let's take time t2 to reach the bottom. So which will reach faster? Suppose they ask, faster means t1 will be smaller or t2 will be smaller. Time to reach is smaller, that is faster, right? So which reaches early. So time we can compare. Time formula, if you see, time 1 by sin theta root under 2 h by g effective here, correct? Isn't it? That's what sin theta g effective. Okay, so sin theta is constant, so height is also same. Let us say they are dropping from same height. So time is inversely proportional to root of g effective. Now g effective, if you see, g effective you can calculate. So g effective is, if you remember, g by 1 plus I center of mass by mr square. So if you take for solid sphere, then g effective will be, I center of mass will be different, that is 2 by 5, and this will be 2 by 3, right? So this thing is going to change. So let's calculate time t1. So time t1 will be inversely proportional to root under g effective. Now root under g effective, here the factor that is going to come is root under g by 1 plus, this is 2 by 5 mr square, so this will become 2 by 5, right? So therefore t1 will be proportional to this will become 7, right? So root under 5 by say root under, this will become root under 7 by 5g, correct? Isn't it? So 5g will come here and 7 will come out. So similarly you can calculate t2. T2 will be proportional to what? In the same manner you can think of. So here instead of 2 by 5 it will become 2 by 3, right? 2 by 3. So 3 factor will come here, and 2 by 3. Sorry, so here 5 factor will come. 5 factor will come here. Okay, and then what will be this? 2 by 3 it will be. So 5 root 5 will come, and 3g, correct? 5 by 3g, isn't it? Right? Is this correct? So you can see here, once you substitute here, for example here 2 by 5, so it will become root under this 5g will associate with the 5 will associate with g, and 7 root 7 will come. Similarly 2 by 3 will be 3g will come, and 5 will come outside. Okay, so now you can compare this, which is larger, which is smaller. So if you want, you may take ratios also to compare, isn't it? Or here itself you can compare, because this factor I center of mass is larger for hollow sphere. So as this factor is larger, this whole denominator is going to increase, so this will decrease. So for hollow, this I center of mass is larger, so this is going to decrease. So G effective decreases, so time will increase. Correct? So because I center of mass is larger, so G effective will be smaller. Okay, and then if G effective is smaller, time will be, because time is inversely proportional to G effective. Correct? So if you take a hollow and solid, so if you take hollow sphere I center of mass is more. So as this is more, the denominator is large. As denominator is large, G effective is smaller. As G effective is smaller, the time taken is larger. So time taken will be larger for hollow sphere, isn't it? So time t2 will be greater than time t1. Yes, that means this solid sphere, and solid sphere, this I will be smaller, 2 by 5. So if this I is smaller, this term denominator is smaller, then G effective become larger. G effective become larger, time to reach bottom will become smaller. So solid sphere will reach earlier. And here also you can compare. This is 7 by 5 and 5 by 3. You may compare it, right? If you multiply with let us say here 3 you multiply, so 21 factor will come in return, and here 5 multiply 25 will come. T2 is greater than T1. You can compare. Okay, so questions on this you can solve in this manner, right? So and the speed, if they ask which will have larger speed at the bottom, so V is equal to root, again it is proportional to root 2G effective. You can compare the velocity at the bottom when it reaches, right? So I hope you understood. These questions are coming based on this model also. Thank you for your attention.